And this message once again, the following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mail. There are 2 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. So yesterday we finished up section 6.3, looking at a second way of factoring trinomials. Today we're going to go on to 6.4 and look at some special products. Anyway, before we do that, does anyone have any questions from yesterday's homework? If so, now is the time to speak. Perf. Anybody? Anything? Okay, then we'll go on and take a look at section 6.4. All right, first of all, I want to look at some special trinomials. And before we do that, if I take 0 times 0, I get 0 squared or 0. If I take 1 times 1, I get 1 squared or 1. If I take 2 times 2, I get 2 squared or 4. 3 times 3, I get 3 squared or 9. 4 times 4, 4 squared, I get 16. Well, these numbers over here, 0, 1, 4, 9, 16, 25, 36, 49, 64, those are all called perfect squares. A perfect square is a number with 2 identical factors. 16 is 4 times 4, so it has 2 identical factors. Well, a perfect square trinomial is a trinomial with 2 identical factors. So for instance, let's say I take x plus 3 times x plus 3. I would get x squared plus 3x plus 9 by foiling it together, which is x squared plus 6x plus 9. This is a perfect square trinomial because it comes from 2 identical factors. In fact, you could write this like this if you wanted to, but multiplying it out, you would get that. All right, now I want to look at some characteristics of a perfect square trinomial. It's going to have a leading term that is a square. It's going to have an ending term that is also a square. And it's also going to have a plus sign in front of the ending term. Okay, if it meets all 3 of those conditions, then it might be a perfect square trinomial. If it doesn't meet all 3 of those conditions, then it can't be a perfect square trinomial. Let's take another example. Let's say I've got x minus 5 times x minus 5. If I FOIL that together, I get x squared minus 5x plus 25. Combining like terms, I get x squared minus 10x plus 25. It starts with a square, it ends with a square, and in front of the constant, there's a plus sign there. All right? So this could be, and in fact, as we see, it is a perfect square trinomial. All right? Now, so if this isn't a square, or that isn't a square, or that isn't a plus sign, it's not a perfect square trinomial. Why do we care about perfect square trinomials? Well, if we're trying to factor a trinomial, and we can see that it might be a perfect square, it's easier to factor it that way than to use the other methods that we've been looking at. So let me give you some examples here. Okay, let's see. Let's start with this one. M squared plus 12m plus 36. Here is a trinomial. It starts with a perfect square, m times m. It ends with a perfect square, 6 times 6, and there's a plus sign there. So its factors might be that. Again, if it's a perfect square, the factors are identical. Well, how would we get a plus 36 and a plus 12 in the middle? By doing that. So in fact, this is a perfect square trinomial, and the factoring of it is that, or you could write it like this if you wanted to, saying that there are two factors of the quantity m plus 6. Okay, now what if we had this let's try that again, m squared minus 8m plus 36. Okay, now that starts with a square and ends with a square and has a plus sign there. However, let's see, we can't factor it as a perfect square. It might factor some other way, but we would at least try that. It fails, so we would have to say, oh, let's go back and use the other techniques. Okay, all right, let's see here. D squared minus 10d plus 25. Well, that starts with a square up front, ends with a square at the rear. The signs, if it's a perfect square, the signs in the middle have to be identical. Well, let's see, they'd either have to be plus times plus or minus times minus. To get a minus in the middle, we'd have to have two minus signs in the middle there. Does that work? That gives us d squared minus 5d minus 5d plus 25, d squared minus 10d plus 25. So yes, it is a perfect square trinomial, and we can factor it with two identical factors. Let's see, let's take a look at another example. 9x squared minus 48xy plus 64y squared. Let's see, 9x squared would be 3x times 3x, right? 64y squared would be 8y times 8y. So it has a perfect square in the front, perfect square at the end, a plus sign in front of that last term, but the middle term's negative. So for this to work, both binomials would have to have a subtraction sign in the middle. Let's see, that gives us 9x squared minus 24xy minus another 24xy plus 64y squared. Yep, we're going to get that minus 48xy in the middle. So this is a perfect square trinomial with two identical factors. And let's take a look at one more of these. Give you a minute here to get caught up there. Alrighty, we good to go? Super. So let's say I've got this 3v squared minus 42v plus 147. Well, looking at this trinomial, it certainly doesn't have a perfect square up front or at the rear. However, before we look at that, we should see, first of all, is it in standard form? Yes, it is. Is there a greatest common factor? Yeah, we can take out a 3. And then we get, let's see, that would be what, 14v, and that would be plus 49, like that. Okay. Now what's inside? The V's split, the 7, or the 49 splits to 7 and 7. To get a minus, we'd have to have that. That would give us minus 7v, which is minus 14v in the middle. So again, it's a perfect square trinomial once we've taken out the 3. And we could write that like I did there, or like that. Any questions about perfect square trinomials before we go on to the second part of this lesson? All righty. Now we're going to look at binomials. And before we do that, I want to kind of go back to something that would have been in chapter 5, which would have been in a previous math class if you took one here, Math 85. Let's say we've got x plus 3 times x minus 3. So these are not identical factors. In fact, they're called a conjugate pair, where you have the sum of two numbers times the difference of the same two numbers in the same order. When we FOIL them together, we get x squared minus 3x plus 3x minus 9. However, when we combine like terms, the two middle terms cancel each other out, and we're left with another binomial. Now, this is the final answer of FOILing this together, but I want to point out that this quantity is x squared minus 3 squared. Again, we would typically write the final answer x squared minus 9, but this answer is called the difference, as in subtraction, of two squares. This is a square and this is a square. X squared minus 3 squared. So x squared minus 9 is the difference of two squares. Where did that come from? Multiplying together a conjugate pair, a sum of two numbers times the difference of the same two numbers in the same order. Let's look at a couple more examples of that. Let's say I have x minus 5 times x plus 5. So now the negative is in front of the positive. Again, multiplication is commutative, so it doesn't matter which order those factors are in. This gives us x squared plus 5x minus 5x minus 25. The middle two terms cancel out, and we get this, which is what? X squared minus 5 squared. So again, we get the difference of two squares. So if that's true, then what about going the other direction? What if we have a binomial such as x squared minus 49, and we're asked to factor it, okay? It's not a trinomial, so those techniques we've looked at for the last couple of days don't apply here. It's a binomial. It doesn't have a greatest common factor. It doesn't have a negative leading coefficient. So my question is it in fact the difference of two squares? Could we take this and write it like this? Well, x squared could be written as x squared, and 49 could be written as 7 squared. So because that could be written this way, its factors are going to be the sum of these two numbers times the difference of those two numbers. Now, this is not factoring it. This is just confirming that it is the difference of two squares, and then we take the two bases and put them, the sum of them, the difference of them. Any questions about that example? Okay. Let's take a look at another example. H squared minus 144. Well, is that the difference of two squares? Sure, h squared minus 12 squared. 12 times 12 is 144. So the factors would be h plus 12 times h minus 12. Or if you want, you could write h minus 12 times h plus 12. I tend to put the positive term or factor first, but you don't have to. Okay. So if you've got a binomial and you can write it as the difference of two squares, the bases of the squares go here and here, the sum of them, the difference of them. All right. Now, with trinomials, and larger, I've emphasized standard form. With binomials, standard form isn't so important as having it be the difference of something rather than the sum of something or whatever. For instance, take a look at this problem. 49 minus w squared. It's not in standard form, but it is 7 squared minus w squared. So we could write 7 plus w times 7 minus w and have it factored. Now, we can take the same problem and we can put it in standard form first and still get an equivalent answer, but it's a lot more steps. So consider this. I could take 49 minus w squared, put it in standard form, write it as negative w squared plus 49. I could factor out a negative 1 and have w squared minus 49, and then get negative 1 times w plus 7 times w minus 7. This answer is equivalent to that answer. In fact, in the textbook, often they'll have both answers listed. But which one was easier to get? This one. And this answer is just as good as that one. So with binomials, standard form isn't so important as can we write it as the difference? Okay. Here it isn't a difference. Ultimately, when we factor out a negative 1, it makes it so. But again, more steps to do. Let's see here. How about x squared minus 27? That's a binomial. It's got a subtraction sign in the middle. X squared, 27 isn't a square, is it? So we can't factor this, so this would be prime. Okay, doesn't factor. How about, let's see, this one, 2a squared minus 200b squared. So here we have a binomial. It has a subtraction sign in the middle, but 2a squared isn't really a square, and 200b squared isn't really a square either. So at least at this point, it doesn't appear to be the difference of two squares. However, let me erase that. What we can do and should do first is take out a greatest common factor. Now that we've done that, let's see. A squared minus 10b squared. A squared is a squared. 10b squared would be 100b squared. In other words, 10b times 10b would be 100b squared. So I've got 2 times a plus 10b times a minus 10b. So before you make a judgment call as to whether it's the difference of two squares, make sure you've taken out any greatest common factor first. All right. What about x squared plus 16? Well, that's a binomial. X squared is a square. It's x squared. And 16 is a square, 4 squared. So I could write it like that, but that's not a difference. This doesn't factor, so this is prime. I could almost make this statement. I could make the statement, but it's not true. I could almost say, so the sum of two squares is always going to be prime. And that's not true. Let's look at an example. Let's say I had 4x squared plus 64. Okay, 4x squared plus 64. That is the sum of two squares. It's 2x, the quantity squared, plus 8, the quantity squared. It is factorable in that we can take out a greatest common factor. Okay? So this is not prime. However, once we've removed any greatest common factor, if what is left is the sum of two squares, it does not factor any further. But we wouldn't say this was prime because we did take out a greatest common factor. Okay, so this is prime because there's no greatest common factor I can take out, and it's the sum of two squares. This is not prime because I can take out a greatest common factor first. So there's a little distinction there. Be careful with that. Okay, let's see here. What about this? 49d squared minus 16. Is that the difference of two squares? Now, this little thing that I do over here, that is not getting the factors, but that's doing a couple things. It's, first of all, it's convincing myself that yes, it is, or no, it isn't the difference of two squares. And it's also determining what the bases are that are going to go here. Why do I go through that step? Because I've had students do something like this. They'll go 49d squared minus 16, and here they'll put 49d plus 4 minus 4. They forget that not only the d squared has to be broken apart, but the 49 has to be broken apart as well. So my thinking is that by doing this, it forces you to think that through. Okay? All right, let's see here. 4x squared minus z to the fourth power. Well, there's no greatest common factor, but 4 is 2 squared, x squared is x squared, and z to the fourth power could be written as z squared squared. So this becomes that. So now our bases are 2x and z squared. So I've got 2x plus z squared times 2x minus z squared. But wait a minute, maybe we're not done yet. Well, let's see, this is the sum, and there's no greatest common factor, so that couldn't be factored, but oh, this is a difference, and that's a square. Oh, but that's not a square. So we are finished. That would have been our final answer. But let's look at another example. Let's see here. How about x to the fourth power minus 1? So x to the fourth power minus 1 is a binomial. It can be written as x squared squared minus 1 squared. So we can split it up and write it as x squared plus 1 times x squared minus 1. So it factors as the difference of two squares. There was a guy, I think he's still alive, I'm not sure. His name's Yogi Berra, not Yogi Bear, the guy that was the bear with the picnic baskets and all that. But Yogi Berra was a baseball player, and he was known for some sayings that were kind of crazy. And one of them was, "It ain't over till it's over." Okay. All right. Anyway, this ain't over yet. Why not? Because this is also the difference of two squares that could be written by like x squared minus 1 squared. So this sum of two squares doesn't factor further, but this becomes x plus 1, x minus 1. And here again, we have a binomial with a subtraction sign, but that's not the difference of two squares. So this is the final answer. But be careful. X squared plus 1 doesn't factor further. X squared minus 1 does. All righty. Let's see here. Let's do another one kind of like that. Y to the fourth minus 625. So here we go. Let's see. Y to the fourth could be y squared squared. 625. Well, 625 is 25 times 25. So that could be what? 25 squared, right? So that would give us y squared plus 25, y squared minus 25. But wait, there's more, because this could be written as y squared minus 5 squared. So this is going to come down. It doesn't change. But this is going to split up into y plus 5, y minus 5. Now, this is also a binomial with a subtraction sign, but it doesn't factor further. So this would be the final answer. Okay. Any questions about that one? All right, let's see here. How about this? Z squared minus 64. That's a binomial. Is it the difference of two squares? Z squared minus 8 squared. So Z plus 8 times Z minus 8. How about this one? 25 plus B squared. Well, there's no greatest common factor. It's the sum of two squares, but we can't factor it, so that's prime. Looks like rhyme, but that's supposed to be a P there. Okay. There we go. Fix that up a little. Okay, let's see. 5a to the fourth power minus 80b to the fourth power. Well, this is a binomial and it's a difference, but I think there's a greatest common factor we can take out first, because otherwise it's not going to be a difference of two squares, because 5 isn't a square and 80 isn't a square. But if we factor out of 5 first, now what's inside the parentheses? A squared squared minus 4b squared squared. So I have a 5 times a squared plus 4b squared times a squared minus 4b squared. We're still not done yet, though, because look at this one. That could be written as a squared minus 2b, the quantity squared. So I've got 5 times a squared plus 4b squared times a plus 2b, a minus 2b. So you got to keep going as far as you can. But now here, that's a difference, but it's not the difference of two squares. So this would be the final answer. All right. So keep asking yourself, is it done? Is there more that I can do? Etc., etc. Okay. How about this problem? Negative 100t squared plus 20t minus 1. Well, that is not a binomial. That goes back to being a trinomial. And it is in standard form. There's no greatest common factor, but that leading term is negative. So let's factor out a -1 before we do anything else. So that's going to change the sign of each term inside the parentheses. But now looking at that, it starts with a square, ends with a square, and it has a plus sign there. So let's see if that is a perfect square trinomial. We'd have 10t and a 1 and a 1, and oh, a minus and a minus. Does that give us minus 20t in the middle? It sure does. So the final answer could be written that way, or if you wanted to save your pencil lead, you could write it like that as well. Okay. Let's see here. It'll take a minute for you to catch up. I call this catch up with mayo. All right. Let's see here. What about this one? 25y squared plus 16. That's a binomial. There's no greatest common factor. It's not the difference of two squares. It's the sum of two squares, but there's nothing I can do. So that is prime. Okay. This section of problems says, choose the correct method from 6.1, 6.2, 6.3, or 6.4. So they kind of mix them all together. Okay. How about this one? X squared plus x minus 42. That's not a binomial. It's a trinomial. It's not a perfect square, I can tell, because there's got a minus and a 42. There's no greatest common factor. It has a leading coefficient of a 1, so that's going to take us back to 6.2, where we're looking for a product of negative 42 and a sum of 1. So how about 7 and negative 6? Okay, that takes us back to section 6.2.
Excuse me?
Yes.
So I kind of came in late, but how exactly do you know when it's a binomial and a trinomial?
Okay, all right. If a polynomial has one term, like 3x squared, that's called a monomial. If a polynomial has two terms, like 4x minus 7, that's called a binomial. If a polynomial has three terms, like 3x squared minus 7x plus y, that is a trinomial. Okay, so a binomial has two terms. A trinomial has three terms. Think of a bicycle and a tricycle, two terms, three terms. Mono, think of a monocle, one. So a monomial has one term. Does that help?
Yes,
Okay.
thank you.
You bet. So this is a trinomial because it has 1, 2, 3 terms. All right, let's see here. How about this? Rx minus Sx plus R minus S. 4 terms. Think back over the last few days. What have we had that had 4 terms? What did we do with those 4 terms? Factoring by grouping. The greatest common factor of the first 2 terms is x, with a remainder of r minus s. So over here, we should hopefully have a remainder of r minus s, and we could take out a plus 1. Now, technically, I could write just plus that quantity without the 1 there, but I want to put it there to remind me that in this step, I need that 1. I've got to leave that trail of breadcrumbs to get back out of the woods. Remember Hansel and Gretel kind of thing there? All right. Let's see here. How about this one? 3a squared minus 4a minus 4. So here we have a trinomial. It's in standard form, descending powers of a. There's no greatest common factor. It has a positive leading coefficient, so we don't want to factor out a negative 1. But it also has a leading coefficient that's not a 1. So we've either got to use the grouping method or the trial and check method. So what do you want to do? Which one? Grouping or trial and check? You tell me. Anybody? Nobody wants to? Okay.
Grouping.
Grouping? Okay.
Yes.
So A is 3, B is negative 4, and C is -4. The product is A times C, so -12. The sum is B, which is -4. How about -6 and 2? So there's the two numbers whose product is -12 and whose sum is -4. Using the grouping method, recall, we're going to split this middle term into two terms. That's a +2a, whose coefficients are these two numbers. So we've got, let me recopy that, 3a squared minus 6a plus 2a minus 4. Now we'll use factoring by grouping. The greatest common factor of the first two terms is 3a with an a minus 2 left over. So here we have an a minus 2 left over and a +2 outside. So we're going to take out an a minus 2 and have a 3a plus 2 left over. Does anybody want me to go back and use the trial and check method on this problem? Happy to do that if you want. Anybody? Nope. Okay. Let's see here. How about this one? Wait just a minute. We good? Questions, anyone? Good to go on? Okay. 20 in s squared minus 60 in u plus 100 n. This is a trinomial, and it's kind of hard to tell whether it's in standard form or not, because there's several different variables there, but I do see there's a greatest common factor of a 20 in. So I'm going to take out 20 in, and I'll have s squared minus 3u plus 5. Okay. Well, let's see. If I had an S and an S, the product would be 5 and the sum would be -3. But you know what? Even if I could find those, which I can't, I wouldn't be able to get a term with just u in the middle. Now, this isn't prime, but this is as far as we can go. We can take out a greatest common factor, and that's it. Okay. So don't say it's prime, because we did something to it. We just can't do anything more with that trinomial. Okay. All right. So over the weekend, you've got section 6.4 to do. I'll be back this afternoon at 1:15 for an office hour. I'm going to go ahead and stop the video.